You think physics is about answers. You open a textbook, and there they are. Newton's laws, Maxwell's equations, the laws of thermodynamics. Page after page of answers, solutions, formulas that work. You memorize them. You apply them to problems. You get the right result. You think you're learning physics. You're not. You're learning a product, a finished thing, polished and packaged for consumption. But that's not what physics is. That's not what physics has ever been. Physics is about questions. Not the questions you ask to get to an answer and then stop. The questions you ask that lead to more questions. The questions that make you uncomfortable. The questions that reveal how little you actually understand. The questions that don't have answers yet, and maybe never will. Richard Feynman understood this better than almost anyone. He spent his entire career asking questions that everyone else thought were already answered. And in doing so, he discovered things that changed how we understand reality. Let me show you what I mean. Start with something simple. Why do things fall? You already know the answer, right? Gravity. Objects fall because of gravity. Newton told us that centuries ago. There's even an equation. F equals g times m1 times m2 divided by r squared. The gravitational force between two masses. Simple, clean, done. Except that's not an answer. That's a description. It tells you how to calculate the force. It doesn't tell you why the force exists. Feynman would push on this. He'd ask, what is gravity? Not what does it do, what is it? Is it a force that reaches across space? How does the Earth know the moon is there? How does the pull get transmitted? You can say gravitational field, but that's just another word. What is a field? Is it a substance? Is it a distortion? Is it real, or is it just a mathematical convenience? Newton didn't know. He admitted he didn't know. He said, "I frame no hypotheses." The equation worked. It predicted planetary motion with incredible accuracy. But he had no idea what gravity actually was. And here's the thing. Neither did anyone else for 200 years. 200 years of using the equation, teaching the equation, trusting the equation. And nobody knew what gravity actually was. Then Einstein comes along and asks the question again. What is gravity? And he doesn't accept it's a force as an answer. He thinks about it differently. He thinks about falling. If you're in an elevator and the cable snaps, you're in free fall. You don't feel gravity. You feel weightless. The objects around you float. It's as if gravity disappeared. But it didn't disappear. You're still accelerating toward the ground. So why don't you feel it? Einstein's answer turned physics upside down. Gravity isn't a force pulling you down. Gravity is the shape of space-time. Mass bends space-time. And when you fall, you're following the straightest possible path through that curved space. You don't feel anything because you're not being pushed or pulled. You're just moving naturally through geometry. That's general relativity. And it came from asking a question that everyone thought was already answered. This is what physics actually is. It's not collecting answers, it's questioning the answers you already have. It's looking at something everyone accepts and asking, but is that really true? How do we know? What if we're wrong? What happens if we push this idea to its limits? Where does it break? Most people don't want to do this. It's uncomfortable. It feels like you're going backward. You had an answer and now you're questioning it. Why? Because the answer might be incomplete, Because the answer might be wrong in ways you haven't noticed yet. Because there might be something deeper underneath. Feynman did this constantly. Take quantum mechanics. By the time Feynman got to it, quantum mechanics was established. It had been around for 20 years. People were using it. It worked. Schrödinger's equation could predict atomic energy levels. It could explain chemical bonds. It could calculate scattering cross-sections. The math worked. But here's what bothered Feynman. Nobody understood what the math meant. You solve Schrödinger's equation and you get a wave function. What is the wave function? It's not a physical wave like water or sound. It's a mathematical object, a complex number assigned to every point in space. And when you measure something, you square the amplitude of the wave function to get a probability. Why? What's actually happening? Is the wave function real? Does it collapse when you measure it? If so, how? What counts as a measurement? These weren't new questions. Bohr and Einstein had been arguing about them for years, but most physicists had moved on. They said, "Shut up and calculate. The equations work. We can make predictions. We can build technology. Why worry about interpretation?" Feynman didn't accept that. He wanted to understand what was really happening. Not just mathematically, physically. What is the world doing? So he started asking questions. In the double-slit experiment, an electron goes through two slits and creates an interference pattern. How does one electron interfere with itself? Does it go through both slits? Does it go through one slit and somehow know about the other? What's really happening? The standard answer was, you can't ask that question. Quantum mechanics doesn't tell you what path the electron took. It only tells you probabilities for where it ends up. The path isn't defined. Feynman found that unsatisfying. So he developed a completely different way of thinking about quantum mechanics. He said, what if the electron doesn't take one path? What if it takes every possible path simultaneously? Every path from the source to the detector. Straight paths, curved paths, paths that loop back on themselves, paths that go to the moon and back. All of them, at once. And each path contributes a complex number, an amplitude. And when you add up all those amplitudes from all possible paths, you get the wave function. This is path integral formulation. It's mathematically equivalent to Schrödinger's equation. It gives the same predictions, but it provides a completely different way of thinking about what's happening. And it came from asking a question that everyone else had stopped asking. What is the electron actually doing? Now, did Feynman answer the question? No. He provided a different framework for thinking about it. A framework that's incredibly useful. Path integrals are now the standard way to do quantum field theory. They're essential for calculating particle interactions. They're the foundation of modern physics. But they don't tell you what's really happening any more than Schrödinger's equation does. They give you a different way to calculate the same probabilities. The mystery remains, and Feynman knew that. He didn't claim to have solved the measurement problem. He didn't claim to know what the wave function really is. He just provided a new tool, a new way of asking the question. And that's the point. Physics isn't about getting to the final answer and stopping. It's about developing better and better ways to ask the question. Think about what this means. Every major advance in physics came from someone questioning something everyone else accepted. Newton questioned Aristotle's idea that objects need a force to keep moving. He asked, what if an object in motion stays in motion unless something stops it? That led to the first law. Maxwell questioned whether electricity and magnetism were separate phenomena. He asked, what if they're two aspects of the same thing? That led to electromagnetic theory. Einstein questioned whether time is absolute. He asked, What if time is relative, dependent on your motion? That led to special relativity. Each time, the person asking the question was told they were being difficult. They were told the answer was already known. They were told to stop wasting time on solved problems. And each time, the person asking the question uncovered something deeper, something everyone else had missed. This is why Feynman was so insistent that students learn to question. Not to be contrary, not to be annoying, but because questioning is the engine of physics. It's how progress happens. When you accept an answer without questioning it, you stop thinking. You stop looking. You miss things. You miss the gaps in your understanding. You miss the places where the theory doesn't quite work. You miss the opportunities to discover something new. Let me give you a concrete example. Feynman was teaching an introductory physics class at Caltech. He got to the topic of why things reflect light at a certain angle. The standard answer is the law of reflection. The angle of incidence equals the angle of reflection. Simple. It's in every textbook. Students memorize it. They apply it. It works. Done. But Feynman didn't just give them the law. He asked, why? Why does light reflect at that particular angle? What's actually happening? One student might say, well, that's just what light does. Another might say, it's because of the electromagnetic properties of the surface. But those aren't answers. Those are just other ways of stating the observation. They don't explain anything. So Feynman showed them something deeper. He showed them that you can calculate the angle of reflection using path integrals. You consider all possible paths the photon could take from the source to your eye, bouncing off the mirror. Most of those paths don't contribute much because they interfere destructively with nearby paths. But there's one path where all the nearby paths have almost the same length. That's the path where the phases add up constructively. And that path is exactly the one where the angle of incidence equals the angle of reflection. This isn't just a mathematical trick. It's revealing something profound. The light isn't following a single path. It's exploring all paths. And the path we observe, the classical path, is the one where the quantum mechanical amplitudes reinforce each other. The law of reflection isn't a separate rule. It emerges from quantum mechanics. It's a consequence of something deeper. Did this answer why light reflects? No, it pushed the question back to, why do photons take all paths? What does that even mean? How can a single photon explore multiple paths simultaneously? The mystery remains, but now it's a different mystery, a deeper one. And that's progress. Not because you got an answer, but because you asked a better question. This is what frustrates people about Feynman's teaching. He doesn't give you closure. He doesn't give you the satisfaction of a solved problem. He gives you more questions. He makes you uncomfortable. He makes you realize how much you don't understand. And that discomfort is the whole point. That discomfort is where learning happens. Most education works the opposite way. It gives you answers. It makes you feel like you understand. You learn Newton's laws. You solve some problems. You get them right. You feel good. You think you understand motion. But do you? Do you know why Newton's laws work? Do you know where they come from? Do you know where they fail? Probably not. You just know how to apply them. And that's useful. I'm not saying it isn't. But it's not understanding. It's competence. There's a difference. Understanding means you can question, you can probe, you can ask what happens in edge cases. You can see the limits of the theory. You can recognize when something doesn't quite fit. You can wonder if there's something deeper. Competence means you can calculate. You can get the right answer on the test, but you can't see beyond the test. You can't see where the theory is incomplete. Feynman wanted students to understand, not just be competent. And the way to get understanding is to question everything, even things that seem obvious, especially things that seem obvious. Because the things that seem obvious are often the things we've stopped thinking about. And when you stop thinking about something, you stop seeing it clearly. Take energy. Everyone knows what energy is, right? It's the ability to do work. It's conserved. It comes in different forms: kinetic, potential, thermal, chemical. You can convert between forms, but the total amount stays the same. That's the first law of thermodynamics. Energy conservation. Simple, fundamental, true. Except, what is energy? Not what does it do, what is it? You can't point to energy. You can't see it. You can't hold it. It's not a substance. It's not a thing. It's a number, a calculable quantity. When you add up all the different forms of energy in a system, you get a number. And that number doesn't change over time. That's remarkable. But what is it? Why is it conserved? What's the deep reason? Feynman would tell you that energy conservation comes from time symmetry. If the laws of physics are the same today as they were yesterday, then energy is conserved. That's Noether's theorem. It's a deep connection between symmetries and conservation laws. But that just pushes the question back. Why are the laws of physics symmetric in time? Why don't they change? We don't know. We observe that they don't change, and we build theories around that observation. But we don't know why. This is the pattern over and over. You ask why. You get an answer. You ask why about the answer. You get a deeper answer. You keep asking why until you hit something fundamental, something we can't explain in terms of anything simpler. And at that point, you have to say, that's just how the universe is. That's what we observe. We can describe it mathematically. We can test it experimentally. But we can't explain it in terms of something more basic because there isn't anything more basic. And that's okay. That's not a failure. That's bedrock. That's where the questions lead if you keep asking them. But most people stop asking long before they get there. They get an answer that satisfies them and they stop. They don't realize there are more questions underneath. They don't realize how deep the mystery goes. Feynman never stopped asking. He'd take something everyone understood, something in every textbook, and he'd ask, but do we really understand this? Can we think about it differently? Is there another way? What are we assuming? What if that assumption is wrong? He questioned everything, not because he was difficult, because he was curious, because he genuinely wanted to know. And this curiosity led him to discoveries that no one else made. Take quantum electrodynamics. By the late 1940s, quantum mechanics and special relativity had been around for decades. People had been trying to combine them to describe how light and matter interact. But the calculations kept giving infinite results. Nonsense. The theory didn't work, or rather, it worked at low energies but broke down when you tried to calculate precisely. Most physicists were stuck. They had the equations, they understood the principles, but they couldn't make the calculations work. Feynman approached it differently. He went back to basics. He asked, what are we actually trying to calculate? We're trying to calculate the probability that an electron goes from point A to point B and interacts with photons along the way. How can we think about that? What's really happening? He developed his diagrams. Little pictures showing particles moving through space-time, interacting, splitting, combining. Each diagram represents a possible process. Each process contributes to the total amplitude. You add up all the diagrams and you get the answer. The diagrams weren't just pictures. They were a computational tool, a way of organizing the calculation, a way of visualizing what you're doing. And they worked. They gave finite results that matched experiments to incredible precision. But here's what's remarkable. Feynman didn't invent new physics. He didn't change the equations. He just asked a better question. Instead of asking, how do we solve these integrals, he asked, what are we really calculating? What's the physical process? And by asking that question, by going back to the fundamentals, he found a way forward that everyone else had missed. This is the power of questions. The right question can unlock a problem that seemed impossible. The wrong question can keep you stuck forever. And most of the time, we're asking the wrong questions. We're asking, how do I get the answer? We should be asking, what am I actually trying to understand? Feynman's diagrams are now ubiquitous. Every particle physicist uses them. They're in every textbook. They're the standard way to do calculations in quantum field theory. But they came from questioning. They came from refusing to accept that the problem was just hard. They came from asking, is there a better way to think about this? This is what education should be. Not memorizing answers, learning to ask questions, learning to see what you don't understand, learning to be comfortable with uncertainty, learning to think, not just calculate. But that's not what most education is. Most education is about answers. Here's the formula. Here's the method. Apply it to this problem. Get the right answer. Move on. And students learn to do that efficiently. They learn to recognize problem types. They learn which formula to use. They get good at getting the right answer. But they never learn to question. They never learn to think about what the formula means. They never learn to wonder if there's something deeper. Feynman hated this. He saw it in his students at Caltech. Bright students, top of their class. But they couldn't think. They could solve textbook problems. But if you asked them a question that wasn't in the textbook, they were lost. If you asked them to explain what a formula meant physically, they couldn't do it. They had memorized procedures, not understanding. He saw the same thing in Brazil. He was invited to teach there for a while, and he noticed the students could recite everything. They knew all the definitions. They could state all the laws. But they didn't understand any of it. They couldn't apply it to a new situation. They couldn't see the connection between the physics and the real world. They had been taught to memorize, not to think. And memorization is not physics. It's the opposite of physics. Physics is about looking at the world and asking why. Why does the sky change color at sunset? Why do ice cubes float? Why does a spinning top stay upright? These are simple questions. Children ask them. But the answers are deep. They involve light scattering, molecular structure, angular momentum. And if you really dig into any of these questions, you find layers of complexity. You find that the simple question opens up into a whole field of study. But here's the key. You only find that if you ask the question. If you just accept that the sky is blue because that's what skies do, you learn nothing. If you ask why, and you pursue that question, you discover Rayleigh scattering. You discover that short wavelengths scatter more than long wavelengths. You discover why the sky is blue during the day and red at sunset. You discover why space looks black. You discover something about the nature of light and atmosphere, all from one question. And then, if you keep asking, you discover more. Why does short wavelength light scatter more? That takes you into electromagnetism. Why do molecules respond differently to different frequencies? That takes you into quantum mechanics. Why do electrons have the energy levels they do? That takes you into atomic theory, wave equations, probability amplitudes. One question leads to another, leads to another. There's no end. There's always something deeper to ask. This is why Feynman said, physics is about questions, not answers, because the questions never end. Every answer opens up new questions, and that's not a bug, that's a feature. That's how knowledge grows. That's how understanding deepens. You don't arrive at the final answer and stop. You arrive at a better understanding, which lets you ask better questions, which leads to even better understanding. It's a spiral, always going deeper, always revealing more structure. But most people want closure. They want to ask a question, get an answer, and be done. They want to feel like they understand. They want the satisfaction of completion. And education gives them that. It gives them answers. It gives them closure. It makes them feel smart. But it's a false satisfaction, because they don't really understand. They just think they do. And thinking you understand when you don't is worse than knowing you don't understand. Because when you know you don't understand, you keep looking. When you think you understand, you stop. Feynman never stopped. Even when he knew more than almost anyone else on the planet, he still questioned. He still wondered. He still admitted when he didn't know something. He never pretended to have all the answers. And that humility, that willingness to say, I don't know, that's what made him great. Not his intelligence, not his mathematical ability, his curiosity, his refusal to stop asking questions. This is the lesson. This is what physics really is. It's not a collection of formulas and laws. It's a way of thinking. It's a way of questioning. It's a way of looking at the world and refusing to accept things at face value. It's a discipline of curiosity. And that discipline is what leads to discovery. Not memorization, not calculation. Questioning, always questioning, never satisfied. Always wondering if there's something deeper, something we're missing, something we haven't thought of yet. So, when someone asks you, what is physics? Don't tell them it's the study of matter and energy. Don't tell them it's equations and experiments. Tell them it's the art of asking why. Tell them it's the practice of never being satisfied with the answers you have. Tell them it's the recognition that every answer is provisional. Every theory is incomplete. Every understanding is just the beginning of deeper understanding. That's physics. That's what Feynman knew. That's what he tried to teach. Not answers, questions. Because in the end, the questions are what matter. The questions are what drive us forward. The questions are what make us see the world as it really is, not as we imagine it to be. And seeing the world as it really is, that's the whole point.